All right, I'm going to go over the second FRQ here. So the first part of the question gives you two Lewis structures, and it's asking you to explain why the diagram on the left, this one, is a better representation for the bonding and the acid, and then justify your choice based on formal charges. So already it's telling you you need to assign the formal charge. So when we're looking at this molecule right here, okay, so to get your formal charge, you're going to take the number of valence electrons, and then you're going to subtract the number of bonds. There's one bond on this oxygen right here, and then the number of lone electrons, so 2, 4, 6. So the oxygen should be -1. Now let's do nitrogen. So nitrogen has 5 valence electrons, and there are 1, 2, 3, 4 bonds, 0 lone electrons, so that's going to give me a charge of +1, not a charge, but a formal charge, yeah. Then carbon, okay, so we have 4 valence electrons, and we have 4 bonds, no lone electrons, so 0. And then hydrogen has 1 valence electron, there's 1 bond, 0 lone electrons, so that one should also be 0. Okay, so these are the formal charges for this particular molecule. Let's look at the other one, the other option. So they drew 2 Lewis structures. They're asking which one is more probable. So we can explain that with formal charge. So let's calculate out the formal charges first. So let's do oxygen. Oxygen is 6 minus the 2 bonds plus the 4 lone electrons, so it's 0 here. Let's do nitrogen. Well, there's 5 valence electrons, and there are 4 bonds, 0 lone electrons, so that's going to give me +1. Then the next one for carbon, there are 4 valence electrons, and for this one there are 3 bonds and 2 lone electrons. So that one will give me -1. And then let's do hydrogen. Hydrogen should be the same thing. 1 valence electron minus the 1 bond would be 0. Okay, so now the rules for formal charge are this. Okay, so first of all of them need to add up to the charge of the entire molecule. So they do, they add up to 0. Same thing here, everything adds up to 0. The other rule is that you want to give your more negative formal charges to your more electronegative atoms. And then there's the problem. So when I look at this one right here, the negative formal charge is going to the oxygen, which is the most electronegative atom of those 4. Then when we look over here, the negative formal charge is going to carbon. Well, oxygen is more electronegative, so it does make more sense that the oxygen gets that negative formal charge. This is the better Lewis structure because of that. So you would get 1 point for assigning oxidation states correctly. You get another point for explaining, well, this is going to be the better structure because the formal charge of the oxygen is negative, and that's the most electronegative atom. All right, so let's look at the next part. Okay, so the next one involves bond enthalpy. So you've got these 2 compounds here, which that's different than up here. So we have this reaction where this will go to this, and we have the structures shown. Then it gives us the bond enthalpy, and then it says that use the Lewis dot diagrams to determine the delta H for this reaction. Well, there's only 2 compounds, so when we determine the delta H here, we're given bond enthalpies. So you add up the bond enthalpies for the products, you add up the bond enthalpies for the reactants, and then if you have reactants, that means you're breaking the bonds, which makes delta H positive for that. The bond enthalpy will be positive to break bonds. The bond enthalpy should be negative for bonds that are being formed. So it takes energy to break bonds. Energy is released when you make the new bonds. So let's look at the bonds broken. So I have an HC bond, and that HC bond is 413. There's only one of those. I also have a C triple N, and that's going to be 891 multiplied by 1 because there's only one of those. And then I have an NO, and that's going to be 201. And again, I only have one of those. So when I add that up together, I get 1505. All right, so now the next one, we're going to do the bonds formed. So look at your product. So now I have an HN bond. That is 391. There's only one of those. Then you're going to make a C double bonding to an N. That will be 615. There's only one of those. And then I have a C double bonding to an O. That's 745. There's only one of those. So when I add these together, I'm going to get 1751. Okay, so you get a point just for saying that this is negative, or if you subtract it. So if you take 1505 minus this, because you're indicating that you understand that this is going to release energy, this requires energy, you get a point just for that point. Now, if you get the correct answer, you get 2 full points. So if I'm going to take negative 1750, and then add 1505, I should get negative 246 kilojoules per mole. So if you have this as your answer with the negative sign, that gives you the full 2 points. But let's say that you don't have 246, but you did indicate somewhere that you understood that the bonds formed will be negative or exothermic, then you'd get a point for that. All right, so a student claims that the delta S for the reaction is close to 0. Explain why the student's claim is accurate. So delta S, remember, deals with 2 things. So entropy is disorder. So entropy increases if you increase the number of molecules, okay? And also if you change the state of matter. So if you go from a liquid to a gas state, that's going to increase your entropy. So we're going to look at those 2 things, gas to gas, okay? And then we also have 1 molecule to 1 molecule. Well, I would think that entropy hasn't really changed much. So delta S is probably close to 0 because of the fact that states of matter have not changed and we've gone from 1 molecule to 1 molecule. You've just simply rearranged the atoms. So you get the point for explaining it's close to 0 because states of matter don't change, number of molecules do not change. All right, so which species is present in higher concentration at equilibrium at 298? Justify your answer in terms of thermodynamically favorability. Okay, essentially, and the equilibrium constant. Essentially what you're looking at here is it doesn't give you the value of K, it doesn't tell you if it's larger than 1 or greater or less than 1. If K is larger than 1, that means you have lots of products. That indicates that it's thermodynamically favored. So if it's thermodynamically favored, that means that delta G would be negative. So is there a way for us to determine whether delta G would be negative or positive? Well, delta G is equal to delta H minus T times this. Well, okay, I know what delta H is. That's negative 246. It does tell me the temperature, but if delta S is close to 0, that means that temperature multiplied by that would be 0. So delta G should be approximately this, but that's not what's important. It's the fact that it's negative. So since it's negative, that indicates that it's thermodynamically favored, which means that K should be larger than 1. So I should have more products. When K is larger than 1, that means I make a lot of products because the K expression is products over reactants. All right, so let's look at the next part. Okay, so This one, it looks like a kinetics problem. So it gives you a reaction, and then a student studying the decomposition reaction runs the reaction at 90 degrees. The student collects the data on the concentration of urea as a function of time, shown by the data. So it's giving time versus concentration. So the student proposes that the rate is equal to K times the reactant to the first. So if we're talking about to the first, we're going to look at the graph. There's actually a couple different things that you can do here. So remember, for kinetics, if we have a graph and we are given concentration versus time, and it's straight, that means it's zero order. All right, now if I have the natural log of the concentration versus time, and that is straight, that is going to be first order. And then if I graph it and then I have concentration, or 1 over concentration, I'm sorry, with time, and then I get a straight line, that's going to be second order. All right, so when I look at this, this is curved, so that means that if I have a curved line, it's not zero order when I graph concentration versus time. So first versus second. So one of the things that you could do is you could say, okay, let me go ahead and take the natural log of these numbers. So if I have the natural log of 0.1, the natural log of 0.07, the natural log of 0.05. So if I were to do that, okay, what I'm going to see is that this is negative 2.3. This is negative 2.66 roughly. And then this is going to be negative 3 roughly. Like, they're pretty close. So I'm noticing, okay, it goes up by 0.33 every time. So if I continue to do that, I could graph it with my graphing calculator and get a straight line, and then I would know, okay, it's first order. But I could also look at it and say, okay, it's going up by the same number every time, which means my slope is constant. So that would give me a straight line. So that's one thing that you can do. The other thing you can do is you can look at the half-life. Okay, so after 10 minutes goes by, so we go from 0.1 to roughly 0.05. Okay, so half of it's gone after 10 hours. Let's look at the next 10 hours. I have 0.05 and close to 0.025. Well, again, it went down by half. The half-life is constant. So if half-life, if that is constant, that means it's first order, because first order reactions have a constant half-life. So two ways that you could tell it. Take the natural log of these numbers. Are they going down or up by the same number every single time? That means it's first order. Or you can graph it when you get a straight line, it's first order. Or you can look at the half-life. The half-life is constant every 10 hours. So every 10 hours it goes down by half. So that's what half-life is, remember? So you could have used either explanation for that. For the next part, use the proposed rate law and the student's results to determine the value of the rate law constant. So if you go into your data book, okay, your data book has a half-life equation. So in the data book under kinetics, you're going to see that your half-life, or well, it has an equation involving half-life. It's 0.693 divided by the half-life. So if I look at the graph, I can tell that it goes down by half every 10 hours. So my half-life is 10 hours. So I just plug that in, 0.693 divided by 10 hours. Okay, so K is going to give me 0.069. And then now for the units, because it does mention the units and you have to have the units, otherwise you don't get the point. So you know it's first order. Okay, so it is going to be 1 over whatever the time unit is, which happens to be an hour. Now, the other thing that you could do is you say, okay, well, I know it's first order. Okay, so when I'm looking at this, my rate, if I go back to the data, my rate okay, so I am measuring the concentration versus the hour. So my rate unit would be the molarity divided by hours. I don't know what K is, and then I know that molarity is big M. Well, what do I need here to get to this point? Well, I have a big M, and I don't want to get rid of it. I don't have the time unit, so I need to have 1 over an hour. That's my unit. All right, the final question is asking about how you would measure the order for hydroxide. So the student learns that the decomposition reaction was run in a solution with a pH of 13, so it's a basic solution. So briefly describe an experiment including the initial conditions that you would change and the data you would gather to determine whether the rate of the reaction depends on hydroxide. So really, it's asking, is hydroxide part of the mechanism? Because you know that if it's in a basic solution, it contains hydroxide. So one of the things you could do is you could perform the experiment at a different concentration of hydroxide. So you know that the pH is 13, change the pH and make it a different amount. So you're changing the concentration of hydroxide. And then measure how that impacted the rate of your product. Okay, so how does that change over time? And then everything else should be held constant, like the temperature. You can't change the temperature because you know that's going to change the value of K.